Welcome everyone to week 3. We will be going over gas laws this week, and we're going to be going over chapter 9 of the textbook. Oh, I'm sorry if it's cutting in and out like last time. Is it okay now? Yeah, let me know if it continues. I'll try to see if the audio gets better at all. But other than that, yeah, let's get right into it. We will be starting on question 27. And it reads, a spray can is used until it is empty, except for the propellant gas, which has a pressure of 1,344 torr at 23 degrees Celsius. If the can is thrown into a fire at temperature 475 degrees Celsius, what will be the temperature what will be the pressure in the hot can? Okay, so for this problem, we will be using an equation derived from the equation PIV-NERT, which is written like this: PV equals nRT. And so when you're using two different changes in something, and the pressure and the temperature is changing here, the other variables in the equation, if they're staying the same, all you have to do is represent those two that are changing to the other two. So what that looks like is so if it's pressure and temperature, to get temperature to the other side, you would have to divide by it. So it's going to be P over T1 equals P2 T2. So that's what that looks like when comparing two things that are changing. So all we have to do is just plug in our values. So pressure 1 is going to, or you can just select whichever one you want. As 1 and 2, just keep it consistent. So 1 has a pressure of 1,344, and then 23 degrees Celsius, and then 475 degrees Celsius. And so we also have to convert this into Kelvin. So to do that, we just add 273.15 degrees. But since we're solving for the final pressure, I'm just going to have this as P1 that we're solving for. So I'm just going to multiply by T1. So now we are solving for the final pressure. So now we can plug in our values. So for P2, we'll put the 1344. T1, that is going to be the final, so that's the matching one of the final pressure and temperature. That's going to be 475, but we add 273.15 to make it in Kelvin, and then divided by the initial temperature, which is 23 degrees Celsius plus 273.15 to get into Kelvin units. And then when we solve that out, it is going to be in 3,400 torr pressure. So that is the answer for this one. It's pretty simple. You just have to plug in, your initial pressure, initial temperature, and then what it changes to with the other two ones. And so that's the answer for the first problem. So let's move on to 31. So 31 reads, a weather balloon contains 8.80 moles of helium at a pressure of 0.992 atmospheres and a temperature of 25 degrees Celsius at ground level. What is the volume of the balloon under these conditions? Okay, so we are given, I believe, three values of what we need to put into our equation, and it's the same one as before. PV equals nRT, and we have the amount of moles, so that's the 8.80. We have the temperature, and so that's 25 degrees Celsius, but to get into Kelvin, you add 273. We know the R value, that's just a constant, and since we're working with atmospheres, we're working with the R constant that matches that, which is 0.08206, and the units of that is liter atmosphere mole K. So this constant is just put into this equation and it completely cancels out. So that's why it has all 4 units in it. And we're solving for the volume. and we know the pressure to be 0.992. So if we're solving for the volume, all we have to do is divide by P, and so we'll get volume equals nRT divided by P, and so now all we have to do is plug in all of those values that we just solved for. So N is 8.80, R is 0.08206, T is 25 plus 273.15, and that's divided by the pressure, which is 0.992. And so this will all cancel out into units of liters. So the answer to this one is going to be 220 liters. So it's kind of like just solving the equation for what you want to find. Since it's volume, we want to divide to get volume on one side, and then you just plug and chug. You just put all of those values that you want to find. Okay, let's move on to 32, and let me know if you have any questions as well. But yeah, so 32, and I'll leave this up here if you're still looking at it as well. 32 says the volume of an automobile airbag was 66.8 liters when inflated at 25 degrees Celsius with 77.8 grams of nitrogen gas. What was the pressure in the bag in kilopascals? Okay, so it is going to be asking for the pressure. So before we start anything, let's solve or let's divide and get pressure on one side from PivNert. So that's what I call it. PV equals nRT. And so dividing by volume on both sides will get us pressure. So that's going to be P equals nRT divided by V. So we are given the volume, which is this right here, 66.8 liters. We're giving the temperature, so the temperature is 25 degrees Celsius, but we're working with Kelvin units, so we'll add 273.15. And the N is the amount of moles. So we're not given N directly here, but since we know it's a nitrogen gas and we know the mass of it, we can use the molar mass to then get it into into moles. So we're going to use the grams of nitrogen gas, use the molar mass of nitrogen gas, and then we're left with number of moles. So that's how you solve for N when it's given the mass. And then the R, we'll do that in a second, and before then, the R value is again 0.0206, and this is in liter atmosphere, so we will need to convert from atmospheres to kilopascals right after we get the answer of pressure. And so that's mole K. So let's find the number of moles. So we're given 77.8 grams of N2. It's nitrogen gas, so it's N2. And the molar mass of that is 28.02 grams of N2 per 1 mole of N2. And so dividing that out, we will get 2.7766 moles of N2. So that is our N value right there. So now that we have all of our values written out, we can just, it is having the same problems. Is there any way? Okay, let me see. Let me hear back from my phone if I'm still having a bad connection. I'll just mute myself real quick. It seems to be okay from my end. So this is me talking back. It seems to be okay from my end. So this is me talking back. So it sounds okay on my end when I just pull up my Twitch on my phone, hearing myself back. So it might be yours. If anybody else is having the same problem, it might not be you. It might be me still, but I don't hear the problem that you're talking about. And if it's the recording, the first videos that I was recording in the very beginning, there might be audio issues. because I wasn't using the correct like headset. So now it should be fixed. Past recordings might be a little rough, but the recordings now should be fine. But yeah, let me know if it's still doing that. But anyway, yeah, so now that we know the volume, the temperature, the R value, and N, we can just plug in all these values and solve for the pressure. So it's 2.7766 for N. For the R, it's 0.0. Oh, I wrote down the R value wrong. There we go. 8026. Oh, sorry, 8206. And then the temperature is going to be the 25. Let me just add it down here. So this is going to be the temperature, and then all divided by the volume. And so the volume is 66.8 liters. And so the final pressure for this, on my end, it's very glitchy and cuts out a lot. Okay. Let me pause real quick and see if it's still doing it. I'll be back in around like a couple of minutes. Okay. Yes, to answer your question, I apologize for this kind of format. Um, I'm not doing this on Zoom because I was hired through the Learning Center to stream on Twitch. So this is the way my position is. Um, so it is unfortunate that this is only this way of talking. You can't talk back directly. But I will post these recordings on YouTube so you can always watch them back as well. Is the audio a little bit better by chance? Okay. Well, I do see your comment. I'll let them know that maybe we can switch over to Zoom instead of Twitch. Um, but yeah, let's just continue. I think the recording will pick up fine, um, and I'll try to fix it in the future for sure. Okay, let's put down the answer for pressure. And what we are doing right here is getting the answer in atmospheres. So now we will need to convert it to kilopascals. So for every 1 atmosphere, we need to convert this to kilopascals. We will get an answer in 101.325 kilopascals. So that is the conversion between those two units. So we will get a final answer of 103 kilopascals. Okay, let's move on to question 34. So question 34, it says iodine, I2, is a solid at room temperature, but sublimes, converts from a solid into a gas when warmed. It says what is the temperature in a 73.3 milliliter bulb that contains 0.292 grams of iodine gas vapor at a pressure of 0.462 atmospheres. So we are working with a gas, and it gave us grams, so we'll need to convert that into moles. We're giving a pressure and a temperature, so we're already given 3 of the values that we need. So the pressure, let's write down what we have so far. Pressure is 0.462 atmospheres. We know the volume to be 73.3 milliliters, but if we divide by 1,000, we'll get into liters. So that'll just be liters at the end. And so for the R value, we are working with the same one, 0.08206, and the mass is 0.292 grams. So we'll need to convert that into moles. So let's start out with what we're trying to solve for, and it's asking for the final temperature. So if we have the original equation here, PV equals nRT, let's divide for the temperature. So the temperature will equal, if we divide by nR on both sides, so that'll be PV divided by nR, will equal the temperature. So let's plug these in. So the pressure is 0.462. The volume is 0.0, I believe it's 0.0733. The N value we will solve for in a second. And then for R, it is 0.08206. And so that will equal the temperature. And so let's solve for N real quick. So for N, we have the amount of grams first, and then we'll use the molar mass to convert to moles. So 0.292 grams, and then grams per mole, and we're working with iodine gas, so the molar mass of that is 253.8089, 4 grams per 1 mole of iodine gas. And so that will equal the amount of moles, and that's 0.001150472 moles. So that is the mole amount, so all we have to do is just plug it in right there. So solving for all of that, the temperature will end up being 367 degrees Kelvin. So again, all you have to do is really just find what you are getting in the very beginning from the question, identifying it, solving for what or isolating the variable that you're solving for, and just plugging things in. So that's the basic kind of way of going about these kinds of problems. So let's move on to 41. So it says, for a given amount of gas showing ideal behavior, draw labeled graphs of the variation of P with V, the variation V with T, the variation of P with T, and the variation of inverse P with V. Okay, so the first one, the variation of P with V. When we are looking at the original equation that we're working with, Boyle's law, when we have to solve for P and V, you would have to divide it on the other side. So P would have to be 1 over V. So as V goes up, P goes down. So the way that this relationship is, it is inverse. So it is going to look like this, because the pressure, as the volume gets closer and closer to smaller values, because it's 1 divided by it, it's going to get very large when volume is down. Which makes sense, because if you have like a really, really small vessel of some sort, the gas in there is going to go crazy because it's bouncing a bunch because it's in a small volume. So conceptually it works too when you think about it. Let's move on to B, the variation of V with T. Using the same Boyle's law, variation with V with T, the V is right here, T is on the other side, so it's directly proportional. As one goes up, the other one goes up. So this is going to have a linear relationship because of the structure of the equation. Now let's work on the variation of P with T. So P with T is also directly proportional, because P is over here, T is over here, it's directly proportional. So it's also linear. now let's move on to D, the variation of inverse P with V. So the way we're going to go about this one is a little different. Let me just have this little graph up here. So we're working with inverse P with V. And so as we already saw, this equation here, if we have just P and V to isolate it, right, we would just have forget about nRT, it would just be V equals 1 over P, because if we divide both sides by P, for example, right, that's going to cross out, volume, 1 over P. So if we are already working with the inverse of P, that's what we want to find for the graph, this is directly proportional now. So now we will get the same thing that we got for the last two. It is also going to be linear because it is directly proportional to one another. So now let's work on question 49. So question 49 says to calculate the density of Freon 12, this compound right here, at 30 degrees Celsius and at a pressure of 0.954 atmospheres. So this one is a little different because we can work with a shortcut equation, or you can first calculate the mass and then figure out the volume. But we're going to figure out the shortcut method. So we're going to be using the equation, the molar mass is going to be equal to, let's see, equal dRT divided by P. And so the capital M is molar mass. The lowercase d is the density, and that is what we're trying to solve for here. The R value is just the constant, so it's 0.08206. Temperature is temperature, which is 30 degrees, plus 273.15. And then P is the 0.954 atmospheres. And so since this is Freon, we're going to be using the molar mass of that. But now that we know that we have everything and we know kind of where everything is going, let's solve for D on one side. So let's isolate that. So if we just multiply everything by P and divide by RT, I will show you, because this was P. If we multiply by P and divide by RT, we will cancel all of this out, and then we will be left with D equals PMRT. So let's plug everything in. So the pressure is 0.954. The molar mass of this is going to be 120.91. The R value is 0.08206. The temperature is going to be the 30 plus 273.15. And so when we add up all of those, we should get a value of 4.74 grams per liter. So that is the shortcut method. You can always use PivNert and find the mass and then divide it by, or use the mass that it gives you, right? Or convert the amount of moles that you get into grams and then divide it by the liters. You can always do that, but this is the easier method of using this equation. It's a shortcut. So let's move on to question 52. So question 52 says, what is the molar mass of a gas if 0.0494 grams of the gas occupies a volume of 0.1 liters at a temperature of 26 degrees Celsius and a pressure of 307 torr pressure? So let's write down, if we have everything, try to figure this out first. So it is asking for the molar mass first off. So we can use the shortcut method that we just used. So let's write down that equation. So the molar mass equals dRT divided by P. So we're given the temperature right here. We're given the pressure right here. We know the R constant, that's just a constant value. And we have the density because we can divide the grams and the volume, because density is mass over volume. So that's where the density can come from, and then we will figure out the molar mass from calculating that all out. So let's write down all of those values. So first let's write down the D. So D is mass over volume. So it's 0.0494 grams that we're working with within a 0.100 liter volume. And then the constant R value is going to be still the 0.8206. The temperature is 26 degrees Celsius. And then we add the 273.15 for Kelvin, and then divided by the pressure, which is 307 torr. And we have to make sure that our pressure units are checking out, because this constant that we're working with, again, is in pressure units of atmospheres. So we will need to convert this to torr in order to do that. So this 307 right here, we can convert to torr, or sorry, to atmospheres. So let's do that right now. So for every 760 torr, there is 1 atmosphere. So that's just a simple conversion to atmospheres right there. And so now our pressure units check out. So now we can just calculate everything, and we will get an answer of 30 grams per mole for this gas. So that's how you solve that one. So now let's move on to question 57. Question 57 says, a 36-liter cylinder of a gas used for calibration of blood gas analyzers and medical laboratories contains 350 grams of CO2, 805 grams of O2, and 4,880 grams of N2. At 25 degrees Celsius, what is the pressure in the cylinder and atmospheres? Okay, so we can first know that this is a 36 liter volume. It's using all of these grams of all these different gases, and so since they're all together, we can convert all of those grams into moles using each of their molar masses. So let's do that right now. So we have 350 grams of CO2, and so the molar mass of that is 44.01 grams per 1 mole. Let's just set up each one of these. And then 805 grams of O2 will have a molar mass of 31.999 grams per 1 mole. And then N2 is going to be 4,880 grams of N2. And that has a molar mass of 28.013 grams, or 4 grams per 1 mole. And after we calculate all of those, we'll get a value of 7.95 moles of CO2, 25.157 moles of O2, and then 174.2 moles of N2. And so when we add up all of those together, that is going to be the total amount of moles. And so we will get a value of 207.31 total moles of everything. Okay, so we have the moles in check, we have the volume, and then it is at a temperature of 25 degrees. And so now we are trying to figure out the pressure. And so that equation will be P equals nRT divided by V. And so now we just plug in all of those values. So the N goes there. The R value is again 0.08206. The temperature we have and the volume we have. So I'm just going to tell you the answer that you get when you plug in all those values. It'll be 140 atmosphere pressure. And because our R constant is in pressure units of atmospheres, that's the pressure that we will get in that unit. So that is how you do that one. So let's move on to the next one. I believe we have a few more problems to go as well. So let's read this one. Okay, so we have 63. It says a sample of carbon monoxide was collected over water at a total pressure of 756 torr and a temperature of 18 degrees Celsius. What is the pressure of the carbon? Okay, for this one, when you go to the table, it will tell you that for specifically the carbon, not for the carbon monoxide, but for the water, water vapor at that temperature is 15.5, sorry. So it's PW, we'll call it, is 15.5 torr. And so that's at 18 degrees Celsius. And so for the total pressure, P total, is 756 torr. And so since we're working with two different gases here, the P total is going to equal the PW plus P of the carbon monoxide. So let's write CM. Oopsie. There we go. So the total is going to be of those two gases. So all we have to do is just solve for the pressure of the PCM. So to solve for that, we just do some algebra, and PCM will equal PW minus P total minus PW. And to solve for that, we just have to plug in the values. So that's 756 minus 15.5. And so we will get an answer of 740 torr. And so basically it's easier than you think to solve for this because there's only one unit to work with here, and since we have a total of only two, you just calculate those two that make up the total. So let's move on to question 65. It says Joseph Priestley first prepared pure oxygen by heating mercuric oxide, HGO, that equation right there, or that reaction. It says outline the steps necessary to answer the following question. What volume of O2 at 23 degrees Celsius and a 0.975 atmosphere is produced by the decomposition of 5.36 grams of HGO? Okay, so in order to solve this problem, we first have to use the amount of mass that we get from the HGO. So that is the first thing that we need to do, use the mass of HGO. And how we use it is we need to convert that into moles of HGO produced. And once we have moles of HGO, now we can convert it to how much HGO to O2 in terms of moles is produced from the reaction. So this reaction equation they gave us here, for every 2 moles of HGO, there's 1 mole of 1 O2 gas formed. So we will need to use that conversion there. So we'll convert it to moles O2. And then we will insert that, since we'll get the moles of O2, into the equation. And so since Pivnert, and since we're solving for the volume, the equation will be solving for volume. V equals nRT over P. And so we will put the number of moles of O2 as N right here, and then we solve it because we have all of the other variables. We have the temperature, we have the pressure, and we have the constant value. So now let's solve that. So we have the 5.36 grams of HGO, and now let's convert that into moles of HGO. And that's 216.59 grams. That's the molar mass of this. And then for every 2 moles of HGO, we will produce 1 mole, or we will have 1 mole of O2. and the reaction. So solving that will give us 0.0123 73609 moles of O2. Awesome. So now that we have the number of moles, all we have to do is just plug it into this equation up here, and we will solve. So V equals the mole amount, the R value, the temperature, and then divided by the pressure. So calculating all of that out, we will get a value of 0.30 liters because we were solving for volume. So that is how you go about solving that problem. Yeah, let me know if you have any questions about these in the chat. Let's move on to 68. So 68 says, automobile airbags are inflated with nitrogen gas, which is formed by the decomposition of solid sodium azide, or acid. The other product is sodium metal. Calculate the volume of nitrogen gas at 27 degrees Celsius and 756 torr, formed by the decomposition of 125 grams of sodium acid. Okay, so we have to find the volume. That's what we are wanting to find. And we need to know this reaction equation of the NaN3 and sodium metal. We'll need to know how many moles of each for possible conversions. We know the temperature, we know the pressure, and we know the mass. So from the mass, from just the last problem that we just did, we use the mass of the sodium acid and then convert that into the nitrogen gas through molar mass and mole conversions, and then we use the number of moles, and then we insert it into our Pivnert equation to solve for volume, just as we did in the last problem. So the equation that we'll be putting everything into in the end will be V equals nRT over P, and so we're solving for N right now. So to solve for N, we have to first use the mass, like I said. So the 125 grams of sodium acid, so that's NaN3. And so we'll need to convert that into the moles of N2. But before we do that, actually, I forgot, we need to write the reaction equation. So I'm going to go ahead and write this down. So 2NaN3 will produce N2 gas and also the sodium metal that it talked about. So those are the two products from this. And to balance it, we need 2 of the sodium acid, 3 of the nitrogen gas, and 2 sodium. If you want me to go over how to balance it, I can do that as well. But I just wanted to give the equation so we can just work with it. So anyway, let's go back to the mass. So we're going to need to use the molar mass of the NaN3 to convert it into the moles produced. And so that is 65.01 grams. And then from sodium acid, we can convert it to the number of moles of nitrogen gas, because that's what we're solving for here. And so for every 2 moles of NaN3, 3 moles of N2 will be produced. And we will get an answer of 2.88417 moles of N2. So now that we have the number of moles of N2, we can plug it into our equation here, as well as the temperature, the R, and the P values. So let's do that. So V equals the 0.8206, the R value, which is 0.8 or 0.0, sorry, I just wrote down the R value actually. So the R value is out of the way. The N value is 2.88417. Temperature is going to be the 27 degrees plus 273.15 Kelvin. and then divide everything by the p-value, which is going to be the 756 torr, but that is in torr. We need to convert it to atmospheres again, and that conversion is just dividing by 760, and now we will be in atmospheres. And so multiplying everything out, we will get a value of 71 liters for this answer. So that is how we solve this problem. Now let's move on to 81. 81 is a different kind of question, same with 88 and 104 a little bit. We will be working with different rates in molar masses and also van der Waals. So the previous ones were just gas laws, everything is ideal and perfect. The next problems will be a little different. So now let's read this one. So 81 says, a balloon filled with helium gas takes 6 hours to deflate to 50% of its original volume. How will it take for an identical balloon filled with the same volume of hydrogen gas instead of helium, so it's hydrogen gas instead of helium, to decrease its volume by 50%? Okay, so there is an equation for this exact problem, and the equation says rate A divided by rate B equals molar mass B divided by molar mass A, all raised to the 1/2 power. So that is the equation that we are working with here, and so we are finding the rate of rate A, we will call. So rate A is going to be the hydrogen gas, rate B will be the helium gas. So to solve for the rate here, we will get a ratio. So the rate of A and divide by rate B, this will be the ratio between rates. So let's just plug in the molar masses of hydrogen and helium and then get the answer and see what that is. So the molar mass of B, we'll call it the hydrogen, like I was saying. Sorry, I switched them around, but it doesn't really matter which one, just as you know which one is A and B. So 4.0026 is going to be that one, and then 2.01588, which is the hydrogen gas. And so having that power, we will get an answer of 1.40909. So that is the ratio of those two rates. And so for every 1.409 of H2, we will get 1 of helium, because the rate A, we are saying, was hydrogen. And so because this is the rate in between each other, if helium took 6 hours, then for the hydrogen, it is going to be 6 divided by its rate, which is 6.409, which will give us a value of 4.3 hours. So because the rate was faster, we divide by the time it took for the helium, and then we will get the change in the amount of time the hydrogen will take instead of the helium. So first find the ratio, and then we can solve for which specific rate that we are talking about. So let's move on to question 88. So this one says, a gas of unknown identity diffuses at a rate of 83.3 milliliters per S. I believe the S means something here. I don't know specifically. Yeah, in a diffusion apparatus in which carbon dioxide diffuses at a rate of 102. Calculate the molecular mass of the unknown gas. So this one's the same equation that we're working with, we're just solving for something else. So let's write down that equation again. So rate A divided by rate B equals the molar mass of B and the molar mass of A. So since we're solving for the unknown molar mass, we can do some algebra to solve for that. So if we multiply, or if we raise the power on both sides to the power of 2, then we will get mb over ma, and then rate A divided by rate B raised to the power of 2, and then we multiply both sides by ma. So mb, I'm just going to switch this around, just switch sides, so we are solving for mb on the left. We will get an answer of ma times rate A divided by rate B squared. So now we can just plug in everything and then solve for the unknown molar mass. So the molar mass of carbon dioxide is going to be 44.01. The rate A is 83. Actually, let's see if I'm making this consistent. So rate A is going to be, it's going to be 102. And rate B, which is the unknown, which is rate B, is 83.3. So dividing that, multiplying it all out, we will get a molar mass of 66.0 grams per mole of Mb. So that is how we isolate that and solve this problem. Let's move on to, I believe, the last problem of the day. This is problem 104. It says a 0.245 liter flask contains 0.467 moles of CO2 at 159 degrees Celsius. Calculate the pressure using the ideal gas law. So that's the first problem for this. With the ideal gas law, this is going to be the same equation we were working with previously, and that is Pivnert. And so solving for this, we are trying to find the pressure. So this will be P equals nRT divided by V. And so we'll just plug everything in. So N, the amount of moles, is 0.467 from the problem. 0.08206 is the R value. The temperature is 159 plus the 273.15 to convert it to Kelvin, divided by volume, which is 0.245. So solving for all of that, we will get a value of 66.1 atmospheres. Okay. And now let's move on to, just one second here. Number B, or letter B. Now we will be using the van der Waals equation, and so this one is a little bit different because we are accounting for attraction of the molecules and also that the molecules itself takes up space. So those two things are not a part of the ideal situation. So this equation is such: P plus AN squared over V squared. The A is a constant, and then times V minus NB. The B is also a constant, equals nRT. So just as I was saying, this P term, this addition of adding onto that, is accounting for there's going to be attraction of molecules, so there's going to be an increase in pressure. And if there is volume of molecules itself, so let's just say there's 2 liters, but the molecules itself takes up space, it is going to be less than 2 liters. So it's subtracting another term. And the nRT is going to stay the same. So that is the van der Waals equation, and so using the A constant for the CO2, it gives us a value of 3.59. B is 0.0427. So those are the constant values for CO2. And so plugging everything in and solving for P, it will look like this. You divide by this term right here, and then you subtract this one right here, so minus an squared v squared equals p. So let's do that right now. So n is 0.467, 0.08206. Let's move everything over so we have more room. And the temperature is going to be the 159 plus 273.15 divided by the V value, which is the volume, minus N, which is our new constant value that we're working with. And I still need more room. I'll zoom in. And then minus the N, which is 3.59, times 0.467 squared all over 0.245 squared. So solving for P, we will get a value of 58.9 atmospheres. So because our van der Waals equation accounts for less than, it's not ideal, it's accounting for some attraction, it's accounting for stuff taking up space, our pressure is actually less and less than the ideal situation. And so the reason why this could be is because, actually that's the answer for D, or C and D technically. As I was saying, the A term, let's write that down first, is accounting for molecular attraction. The B term is accounting for molecules taking up space. And so the reason why the pressure is different here is because at higher temperatures, this is at a very high temperature, 58.9 atmospheres, then the B term is more dominant because it's the volume that's kind of depending on the pressure change. And so that's why it's more dominant. When there's high pressure, the B term is more dominant. The opposite is true if it's low pressure, the A term is more dominant because of how the attraction and the volume work together. So at high pressure, the B term is more dominant since they change the total volume, or since it changes the total volume. And the term in the denominator has a large effect. And what I mean by that is, going back to this equation, the B is in the denominator, so it's going to have a large impact on the ending pressure here. So that is the answer for, I believe, 104. I'll leave this up if you're still looking those problems over. But that is it for this week. Hopefully if there was any audio issues, it kind of worked itself out in the end. And this recording, as always, will be posted to the PSU Learning Center. And I will see you all next week for week 4 of chemistry material.